Hello, we're doing checkpoint 5.23. They want us to use rectangular, cylindrical, and spherical coordinates to set up the integral from finding the volume of the region inside of the sphere, x squared plus y squared plus z squared is equal to 4, and outside of the cylinder, x squared plus y squared is equal to 1. Let's first work on the rectangular coordinates. And when we're setting up rectangular coordinates, we want to figure out a specific order for this. It looks like there's a flat XY annulus or disc or washer on the XY plane. So I think it'd be good if we go with respect to Z first. And then at this point, let's just do dy dx. Doesn't really matter too much. And we'll use symmetry. We could use symmetry. So let's take advantage of that. Instead of going from the bottom sphere to the top sphere, we can just double it. If we say we're going to multiply by 2, we're going to double that and just go from 0 to the top part of the sphere. So speaking of the 0 to the top part of the sphere, that would be your Z limits. So we'll let Z go from 0, and then the top part of the sphere would be the sphere if you solve for Z. And since we're really just dealing with a positive part, we're going to have a square root of 4 minus x squared minus y squared. From here, we're going to take a look at what's happening on the xy plane. And what's happening on the xy plane is this washer that we had mentioned earlier. Now, dealing with that washer could be kind of difficult, especially if we're doing things in rectangular coordinates. I think it would be a piece of cake if we were doing this in cylindrical or polar coordinates. And just by eyeing this region, it looks like that's the easiest way to go. But if they want us to set this up using rectangular coordinates, we're going to have to split this up into 2 parts. So first of all, what we're going to do is consider breaking this up into 4 pieces, and then remind ourselves that we're going to multiply by 4. So we're going to just work on the area in the first quadrant. So we'll make a note, just first quadrant. And then we're going to say multiply by 4. So we're going to multiply by 2, and then we're going to multiply by 4. So basically what we're going to do is find the volume in the first octant and multiply everything by 8. I guess that's the bottom line. All right, so now that we do that, we're going to need to figure out how to set this up in rectangular coordinates. And with that, if we just zoom in a little bit, what we're going to have to do is we're going to have to break this up into 2 regions. Let's say we're going to integrate first with respect to y, which is kind of like what we mentioned. So with respect to y, we're going to go from the bottom circle. Now that bottom circle, remember, is the circle that's associated with the cylinder. And so if you solve for y there, you're going to get the square root of 1 minus x squared. And then we're going to get the top part of the circle, which is really this thing when z is equal to 0. It's the sphere when z is equal to 0. And if we solve for y there, we're going to get the square root of 4 minus x squared. Now, this is all happening on the z is equal to 0 plane, the xy plane. So that's what we have. And the x limits here will go from 0 to 1 because this is 1 right here. Okay, now beyond that, there's still this much left in the first quadrant. And so we need to figure out what that is in the first quadrant. And so what that's going to be is going to be an integral here where y is going to go from 0 to the top part of that circle. So the top circle, remember, comes from the sphere when z is equal to 0. And so the y limits here go from 0 to 4 minus x squared. And then x this time goes from 1 to 2. And then now we have ourselves two sets of integrals. All right. So the bottom line in rectangular coordinates, we're going to multiply by 2 and then multiply by 4. So the volume will equal to 2 times 4. And then we're going to multiply the integral, triple integral of 1 dv. Now the v is in this case going to be a dz, dy dx. So the z goes from 0 to the square root of 4 minus x squared minus y squared, and then dy. Now this is where we have to split it up into 2. So I'll do this first one, and that's a square root of 1 minus x squared to the square root of 4 minus x squared. And then dx goes from 0 to 1. So that's the first integral. And then we'll do a second integral. Again, the integrand is 1, and we'll have a dz dy dx like we did before. And your z remains the same, going from 0 to 4 minus x squared minus y squared. But this time your y goes from 0 to 4 minus x squared, and then your x goes from 1 to 2. Okay, so this is your integral setup in rectangular coordinates. Okay, now let's move to doing this in cylindrical coordinates. And like I had mentioned, cylindrical coordinates is a nicer, is probably the best way to do this this volume. So cylindrical. And for cylindrical coordinates, we're going to go dz and then dr d theta. It's usually, again, the best way to express your cylindrical coordinates limits. All right, for this, we're going to set up our z the same way. We're also going to consider multiplying by 2. So that will give us the top and the bottom half. We'll just worry about the top half. And then we will set up our limits for z. So z goes from 0 to basically the sphere that we had in rectangular coordinates, except we lose the x and the y and replace that with x squared plus y squared is equal to r squared. So we have 4 minus r squared for that. And now if we focus on this washer, we can easily express that in cylindrical coordinates by letting r go from 1 to 2 and letting theta go from 0 to 2 pi. Okay, and that's it. That's really simple and easy enough to set up. And so we're going to have a triple integral times 2. And the triple integral is going to be 1. And now our dv is going to generate an extra r. So we have to remember that there's an extra r when we switch from rectangular to cylindrical coordinates. We're going to integrate with respect to z first, going from 0 to the square root of 4 minus r squared. I'm going to integrate with respect to r from 1 to 2, and then with respect to theta from 0 to 2 pi. Okay. Again, fairly easy integral to do, a lot easier than that first integral that we would have had to do in like 3 steps or two pretty difficult integrals. All right, now the last one is to try to express this in spherical coordinates. Although there's a sphere involved, that cylinder in the middle makes it a little bit more difficult to deal with. So again, out of these 3 setups, the cylindrical coordinates will be the best. So how are we going to do this in spherical coordinates? we need to express things with respect to rho, phi, and theta. So we have rho, d phi, d theta. And let's see how we're going to set this up. So the rho is the radial distance. And the radial distance, if we take a look at this graph again, the drawing, the radial distance will be going from the cylinder to the sphere. So the sphere is constant. That's easy enough to express. But now we have to try to express this cylinder in terms of rho. What is this cylinder going to be equal to in terms of rho? So with that, we can find a relationship between the radial distance here. We have x squared plus y squared is equal to 1, also known as r squared is equal to 1, or r is equal to 1, is a way we can express this. And then now if we can figure out what r is equal to in spherical coordinates, we can get something going. So r is actually equal to rho times sine phi. Now, if we have that, we can express rho to be equal to r divided by sine phi, or r times the reciprocal of sine is cosecant. And then knowing that r is equal to 1, we can just say rho is equal to cosecant of phi. So that's what this cylinder is actually expressing. All right, so we can use that to be one of our limits for rho. So rho is going to go from here outward, going from cosecant of phi, and then it's going to go to the sphere itself, which is rho squared is equal to 4, and so rho is equal to 2. And our phi, where's our phi going to go from? So the other issue with phi is that we want our phi to go from the intersection of those two objects down to the bottom. So we can go from the intersection on top to the intersection on the bottom, or we can just stop here and find the intersection on top and then just go up to pi over 2. And then if we do that, we just have to remember to double it. And so the intersection of those two would be when x squared plus y squared is equal to 1, and x squared plus y squared plus z squared is equal to 4. And so if I replace this with 1 and then subtract, so I get z squared is equal to 3. Then I have a value for z, but I need to express z in terms of, I have to express z in terms of phi. So z is actually rho times cosine phi. That's one of the transformations that we have. And so if we replace this with the square root of 3, square root of 3 is equal to rho cosine phi, and then we'll divide by rho. Well, in that intersection that we're looking at, we can divide by rho, but rho is equal to cosine or cosecant phi. So let's write this as square root of 3 is equal to cosecant phi, which is again 1 over sine phi times cosine phi. And so we're going to get cosine over sine is tangent or cotangent. So cotan phi is equal to square root of 3. And so the arc cotangent actually this, it's easier, I think, to express things in terms of tangent. So let's say tan phi is equal to 1 over square root of 3. So that's, we can get that easier in terms of the calculations. So phi is equal to the arc tan of 1 over root 3. I think that's a specific angle. We can figure that out. So that is the intersection over here of that sphere. And see, arctan is cosine over sine. Well, let's see. We can look at this as cotangent is cosine phi over sine phi. And so this is root 3 over 1. So when cosine is square root of 3 and sine is 1 or 1/2 and root 3 over 2, sine is 1/2 at pi over 6. And cosine is root 3 over 2 at pi over 6. So I think that is going to give us a phi value of pi over 6. So your phi then goes from pi over 6 to pi over 2. And by doing this, we're going to make a note for ourselves to say that only went to the xy plane, so we're going to multiply this by 2. All right, so that gives the top part. And now if we let theta go all the way around, then we're going to have the whole top part. So from 0 to 2 pi. Okay. So at least we still have one integral. It was really difficult to figure out these values, but I think we got it here. And our volume then will be multiplied by 2. We're going to have a triple integral. 1. Now to go from Cartesian to spherical, we're going to have a rho squared sine phi. So that's just automatically generated, or that's like your differential. And then we decided to go rho first, and that rho goes from cosecant phi to 2. And then our phi goes from pi over 6 to pi over 2. And then our theta goes all the way around from 0 to 2 pi. All right. Now we probably could just punch this into the calculator, and show that we will get the same answers. But again, this was the easiest setup over here. And so if you had a choice, go with cylindrical coordinates. All right. I hope that helps.